Thank you, Claire and Annie. That was awesome. So next we're going to hear a keynote from Nathaniel Granor. Nathaniel graduated from Yale in 2009 with a Bachelor of Science in Computer Science because it turns out you can't major in a cappella singing. He spent 3 years as a program manager at Microsoft, helping to design and build gorgeous and engaging experiences for a product called SharePoint. During that time, Nathaniel volunteered to help teach computer science at Cleveland High School in South Seattle through a program called TEALS, which he now helps to lead. And over the past 4.5 years, TEALS has grown from a team of 3 people serving 68 high schools to a team of 37 people serving 350 schools in 30 states. Nathaniel believes computer science teaches critical thinking and problem-solving skills that are essential to understanding and participating in the modern world. And all students deserve the opportunity to learn these skills. So let's give it up for Nathaniel.
I don't usually get introduced. I think that's really cool. Kind of weird to hear people talk about you. So, good morning.
Good morning.
You're the brave ones who ventured out in the snow, and I'm really thrilled because I came in last night from New York and I was really scared that I was going to be standing in front of an empty room. So thank you for not being here. So let me just get this kicked off here. That's pretty. Here we go. The what and why of computer science. We're all here to talk about computer science, but we all probably have very different ideas of what that means. Can you hear me all right, or should I grab a microphone? Very good. All right. Cool. So many of you have computers. You probably have phones. Some of you have notebooks and paper. I need you to write something. It could be one word. It could be a paragraph. It could be a picture. What is computer science? I've done this with academics who teach computer science at big universities. I've done this with students. It's always interesting. Just take a minute. Lots of people writing. That's good. Feel free to keep writing. In the meantime, I've got my own little video to show. Yay! I work for a program called TEALS. It's part of Microsoft Philanthropies. We help high schools, specifically high schools, none of you, which I recognize, we'll talk about later, with starting to teach computer science, building and growing computer science programs. And somehow I broke everything. Here we go. So here's a quick video about our program, which we probably won't watch all of, but feel free to keep writing.
The software industry is currently in dire need. Being able to actually have computer science at every high school would be actually an idea, but we are not there yet, and that's what TEALS is trying to change.
TEALS is a program that Microsoft runs where they get professional software developers to come into your classroom and help you teach computer science classes.
If you were coaching a sport, if you had a Major League Baseball player coming in to coach your team, that's really what TEALS is. They're bringing in these industry professionals. Some of them are the best in their business, and bringing them to the students in the classroom.
Teaching computer science is not just about teaching the concepts of computer science. It's a lot more than that. It's a lot about how do you go ahead in your life, how do you break things into parts, and how do you tackle the big stuff.
For my class, there are about 4 software engineers that come, during the week in the morning before class.
One program that they have is the remote teaching program, where it allows you to basically call from home or from the office, Skype in basically to the class.
And you don't need to be a Microsoft employee. You can be any computer science graduate working in any company, and you can still volunteer your time for TEALS.
I think for a lot of our volunteers, they don't have a lot of teaching experience. And at the end of the day, that's okay, because I'm learning computer science and they're learning teaching. And it's a
We'll stop it there, because I'm here and you can hear from me. Okay, that's just a little flavor of what I do in case you're wondering who I am. All right, back to the question that I asked you a few minutes ago. Does someone have something they would like to share?
I'll share.
Go for it. What's your name?
I'm Brian.
Hi, Brian.
I have a cold, sorry. Computer science is learning how to use technology and then make it work for you.
Use technology to make it work for you. Like it. How about someone over here who wrote something that they would care to share? Yeah. What's your name?
Leslie.
Leslie, hi.
Hi. Computer science is the study of the language of computers and how to use that language to create, develop systems and technology to make our lives
Wow.
easier.
So language and creating things to solve problems. I like that. Anyone else? How about one more? I'd love to have 3. Yeah. What's your name?
Amy.
Amy, hi.
Study of current and available technologies and how to apply them to real-world tasks and challenges.
So real world is a big part of it. Tasks, challenges, technology. A lot of themes here. Does anyone see themes that were in what you wrote? Did everyone write something? Maybe not. Okay. So computer science. This turns out to be really, really hard because there is no standard definition of computer science. And there are a lot of related terms that people tend to conflate. Technology education, digital literacy, technology literacy, computer science, coding, programming. What do all these words mean? So I'm going to suggest some definitions. You can keep them or not. Here's one from the Association of Computing Machinery, the ACM, which is the biggest professional organization for computer scientists. They've adopted this definition from a study in 2003. The study of computers and algorithmic processes, including their principles, their hardware and software designs, their implementation, and their impact on society. Okay, it's kind of heady, but we have some things in there. So we know hardware and software, that's important. Algorithms, impact to society. Implementation, that's that real world piece, doing something with them. I like that. But it's not great for students, and it's not great for beginners. So here's one I found on the internet that I kind of like better. Computer science is the study of what machines can do for us. It's a nice, sort of quick way of saying it. Of course, we don't mean any kind of machine, probably. We don't mean, a simple screw or a pulley. That's physics, right? That's not computer science, it's physics. But machines, when we say machines, we mean sort of computational machines. There's this idea of computation. It sounds kind of mathy, but it's not just mathy, because we can compute things that aren't numbers. So I found one other definition that really resonated with me. Computer science is the study of problems, problem solving, and the solutions that come out of the problem solving process. And that again is getting at this idea of what is computation. What is it we use these machines to do? We use them to solve problems. And more than any other discipline that I know of, computer science is about actually the metas. It's zooming out and thinking about how you are solving problems, not just solving them. We solve problems in every subject. We solve problems in English when you're trying to figure out how to write your essay. We solve problems in science when we're trying to run an experiment. We solve problems in foreign languages when I'm trying to figure out how to communicate with someone from another culture. But in computer science, we're actually thinking about the process of solving problems. So these are the definitions I'd like you to consider, at least for the duration of my talk. And maybe you'll keep some pieces of them for later. The other thing, these are sort of top-down definitions, right? This is just sort of, I'm telling you what computer science is. The other thing I think is really important for people who are new to computer science is to learn from example. So I'm going to give you some examples. But first I'd like to get a show of hands. Who in this room would consider themselves an experienced computer scientist or is comfortable with the concepts and ideas of computer science? I'm one. Some of the students should be raising their hands. Great. All right, so most of the people who are attending the conference, that's not why you're here today. You're not. Who would say that they're a total beginner? This is brand new for them today. Awesome. Thank you for being here. And who's somewhere in the middle? Great. All right, so now we've got a sense of who's in the room. So here are some of the things, some of the types of things we do in computer science and we use computer science for. And I have to apologize. I experimented with something new in this presentation, which is inserting animated GIF images into slides. And I was not expecting that there were going to be 412 screens showing you these animations. So it could get overwhelming. We'll see how it goes. So when you think about computer science, one of the first things that comes up is coding, programming, software engineering, the idea of writing computer programs that do something. And so there's a discipline called software engineering. It's the work of software engineers. You might recognize this thing at the top, apps, right? They build apps and applications and programs. This thing in the bottom left is a coding environment where you have tools to help you write the actual software, to write the programs that create software and applications. But there's more to that than in software engineering. There's also product design, user experience, testing, marketing. It's a whole business. So this thing on the right is really cool. I used to work at user experience. Does anyone know what we're looking at in this thing on the right, this animation? Eye tracking. So you've built something, in this case Google, and you're trying to figure out how are people going to use this software. So you get them to sit in front of the screen, and the computer looks at their pupils of their eyes and is able to figure out exactly what they're looking at on the screen, at what time. And so this is a software that's showing you how this person is experiencing your software, what they're looking at. They looked here, then they went over here. Maybe if you move that button around, people will be more likely to see it and press it. Right? So that's part of software engineering, is thinking about the design and how people experience software. It's not just coding. That's going to be a theme for my talk. Here's another area within computer science, data and algorithms. This is kind of busy. I want you to look at this for a minute, and then I'll tell you what it is. This is from one of my favorite websites that's been around for like 10 years, sorting-algorithms.com. Okay, so what we're looking at is we've got a set of bars of different lengths, and they start out mixed up in different ways. So that each row is a different way of mixing up the bars. So the top one, they're randomly mixed up. And in the second one, they're almost sorted in order of length. And in the third one, they're actually totally backwards to start with. And in the third one, they're mostly sorted, but a few are out of place. Right? And then each column is a different method, a different algorithm for putting them in order. And the little red dot is showing you which bar the computer is thinking about at any moment in time. And so they're following a different sequence of commands, a different mechanism for solving the problem of sorting. And as you can tell, those different algorithms have different properties. Some of them are faster. Some of them are slower. Some of them are faster for certain kinds of data, but slower for others. So I'll encourage you, just look at the very first row or column. This is called insertion sort. And the way it works is that the computer starts with the first bar and figures out where that one belongs. And since there's nothing that's been sorted yet, it just belongs at the top. And then it goes to the second bar and says, where does this one belong? Is it bigger or smaller than the first one? It's bigger. It belongs after. So it just picks one at a time and figures out where in the set does it belong. So here it goes. Ready? Okay, next one, next one, next one. It's pretty fast. I'm just going to go down to the next one, figure out where it belongs. I'm going to try it all the way along, and I'm sorting. That's one algorithm for sorting something. And the rest of these columns are other algorithms. So in the study of algorithms, we're looking at how do you solve a particular problem, and what are the properties of that solution? Is it a good solution in general? Is it a good solution for this particular case? And that's algorithms. It can be very mathy. Some real-world applications of algorithms, and I really like to connect computer science to various disciplines because it's really relevant to every discipline. Oh, question?
Sorry, you said that was from your favorite website. What website was that?
Sorting-algorithms.com. Sorting-algorithms.com. It's a very simple website. It's basically just that. It'll tell you a little about the algorithms too if you click on it. So, lest you think computer science is just about STEM, here's a news article from last year where some computer scientists had applied algorithms to look at a corpus of data which was plays by Shakespeare. And then they looked at one particular play that someone had theorized maybe wasn't written by Shakespeare, or maybe someone had collaborated with Shakespeare to write this play, but how could we know? And they applied a computer analysis using data and algorithms. And they decided, based on the data, that they actually do believe that Marlowe did not co-write this play with Shakespeare. They looked at Marlowe's writing and Shakespeare's writing, and they were able to do all kinds of analysis using software. So we can learn something about history, we can learn something about literature. Over on the right, this is a map of New York City, and in fact, this is a really cool map from WNYC, the NPR station in New York City. And you put in your address, and it shows you a heat map of which locations in New York you can get to in what amount of time. So the center where the red is, that's where I live, in Brooklyn. And the red parts are the areas I can get to within 10 minutes on public transit. And as it gets colder and bluer, that's how much longer it would take me to get to different parts of the city. And so if you're thinking about moving, you can try out different places and see, oh my gosh, from here I can get anywhere in half an hour. But from here I can only get to Brooklyn. So, what subject domain is this? I don't know, social studies, sociology, practical life experiences, right? This is using algorithms. How do you figure out the length of time it would take to commute between any 2 points in New York City? It's easy to do for one set of points, but they have to do it for every set of points in New York City. How would you do that? You'd need an algorithm. Another subject in computer science, networks, internet, and devices. So in the top left, this is a little animation showing how a protocol called Tor works. Has anyone heard of Tor? T-O-R. Stands for the onion router. So Tor is a service and a protocol you can find online to protect your privacy in this age of digital surveillance. The way it works is usually when you visit a website, your computer talks to a server, it talks to another server, and serves you that website. In Tor, it intentionally bounces you around between 3 random computers. And it's all encrypted. So anyone who's trying to figure it out only knows that you're talking to some random computers, and they don't know, and that some website is talking to those computers, but they don't know who's accessing what website and which page. And it protects your privacy that way. So interesting developments in the world. Over on the right, this is the new Disney drone light show. They've got 500 little flying drones with LED lights that move in tandem to create here a Christmas tree, but all kinds of different shapes and patterns. In order to do that, those drones have to be networked together. They have to understand where they are in space relative to each of the other devices and be able to correct for wind and be able to correct what happens if one drone blows up and crashes and burns. How are we going to affect the overall image? We use algorithms, we use networking, connected devices. And on the bottom, this is a demo, you can't quite see it, but this woman is wearing a HoloLens. It's a device Microsoft makes for augmented reality, where this device, you put it into a room and it figures out the shape and size of the room, and it's basically puts these things, you're seeing the first person experience that she's seeing as a medical student using a dummy. It's putting more of a realistic model on top of that dummy and different conditions and diseases that she can then click on and zoom in on to understand what would it look like if I were looking at a patient who had bilateral edema. Yeah. So there you go. There's applications in health and medicine. Another area is security and cryptography. This has obviously been a huge area recently. We hear about this in the news all the time, right? New Mac malware linked to Russian hackers of US election. What does that mean? How do you hack a computer? How do you protect against hacking a computer? Anyone know what that thing is in the top right? That logo, that image?
Bitcoin.
Bitcoin just hit $17,000 per Bitcoin.
Down to 13.
Dropped to 13. Ah, damn it. I guess there goes my early retirement. Bitcoin. What is Bitcoin? What is it? I spent my Thanksgiving trying to explain this to my grandfather and several uncles. Seriously, what is Bitcoin? And how are you supposed to figure out if it's a good investment decision if you don't understand what it is? I'm not going to tell you what it is, it would take too long, but that's a subject, an interesting computer. It's related to security and cryptography. That had this huge data breach. Equifax leaked hundreds of millions of social security numbers. How did that happen? And what does it mean? What's the impact of this on society? Right? These are computer science related questions. And finally, this animation on the right is from a video that explains how RSA public key cryptography works. So if you want to communicate with someone on the internet, you're probably aware that other people might be able to listen in. How can you protect against that? Well, you use a code. You scramble your communications. But if I want my friend David to be able to understand what I'm saying, he needs to be able to open that code. But here's the problem. If David lives in Spain and I live in the US, how do we agree on the code to use without sharing it on the internet where anyone could see it? Right? The password. If I just email you my password, anyone who's reading the email will see the password. Well, RSA public key cryptography is a way of getting around that problem, and there's a great metaphor to understand it that involves mixing colors of paint. I'm not going to spoil that for you, but you can find that video on the internet. Just look up RSA paint. Another area that's really big these days, artificial intelligence, robots, machine learning. You've probably heard these words. Here's some incredible examples of things that are happening in this area. So a couple years ago on Jeopardy, remember this? You had a computer that beat the world champions of Jeopardy. Right? Here's a little video, and each time it had a question, it would show you kind of how the computer was thinking. It was considering different possible answers and weighing the probability that each answer was right, and if it thought that it was sure enough that the answer was clock, it would buzz in. And of course, a computer can hit that buzzer a lot faster than a person can. That gave it a pretty big advantage. How did it do that? Artificial intelligence, right? Here's another pretty old video. The first time I saw this robot, I thought it was two people dressed up in a robot suit. It's not, it's a robot. It's a robot that's incredibly versatile and can move around on all kinds of terrain, and it can withstand being kicked and not fall over and collapse. That was 8 years ago, this video is from. Imagine what has changed in the last 8 years with this robot.
Now the robot's kicking the guy.
Yeah, that's right. Yeah, please, for the sake of humanity, please don't kick robots. For all of our sakes. Here's a new technology. You can open up Skype and communicate with anyone anywhere in the world, and there's about, right now, 10 languages. You talk in English, it will listen to your English and translate it into spoken Mandarin in this case, and say it to the other person who can then speak back. It also translates it to text. It's not 100% accurate, but it's pretty darn good. That's like Star Trek for me. Like I was growing up, like Universal Translator. I can't believe this stuff. That's on Skype. You can do that. You can, if you have Skype, just open up Skype and you can. There's like a plugin you put in. It does that. And here's another one we hear about all the time today: self-driving cars. So in this video, on the left, here's the actual cockpit of the car. You see that the person isn't doing anything, and on the right, these are actually different representations of how the car is seeing the world around it and thinking and making decisions. So you sort of start to understand what the car understands, right? It's understanding that these are different objects. It's trying to figure out which of these objects pose an obstacle, pose a threat, and analyze them and make decisions in real time. Self-driving cars are real. They exist. Right now, they're on the roads, right? There's probably more regulatory hurdles to seeing them than there are technological hurdles. So these are some of the areas in computer science. There's a lot more, but it's not coding. Coding is just the tool. Coding is how we start thinking about how to create all of this. Computer science is a horizontal. There was a great paper about 6 years ago called "Software is Eating the World." I always find it funny when people talk about tech companies. Microsoft's a tech company. There are some. Microsoft, Google, these are technology companies. Every company is a tech company now, right? Name me a single company in the top, what is it, the S&P 500 that doesn't employ computer scientists. They all do. Because software is just a way of solving problems, computable problems. So this is a little bit of the what of computer science. What is it that this is for? What do we use this for? I hope I've convinced you that pretty much whatever it is your students might be interested in the future, whether it's art and music, or literature, or civic living, right? There's applications in computer science that they're going to want to have access to make an impact in those spaces. And that really starts getting to the why. Why is it important that students get exposed to computer science and get exposed early? Before I start to answer that question, let me ask you another question that could seem a little snarky. Why is it important that we expose students to biology? They're not all going to become doctors. That's a real question.
It gives them a foundation for building whatever it is they want to learn about. So if you understand the systems of organisms, you can apply that in other disciplines.
Yeah, so one reason is there might be things that you learn about in biology that are applicable to lots of other subjects. Yeah, Dave?
Yeah, there are processes of categorization or understanding or systems thinking or being able to like dive deep and like doing research and like into any subject that are commonly employed.
Yeah, so there are certain basic skills and basic literacies that we've decided that through studying biology you can access. There's other reasons though. There's some really practical reasons to study biology.
So you have an understanding of your own body and how it works.
Your own body and the world, like to you know, what does it mean when I go to the doctor and they say I have a virus versus I have an infection, right? That's really important knowledge in the 21st century, or 20th century, right? Vaccines. Should I vaccinate my child? Yes.
Yes.
Sorry, politics aside. Why is that political? I don't know. So computer science. Here are the 3 reasons I give when people ask me why computer science is important for students. Now the first one comes up a lot, especially when you're talking to like the politicians, the administrators, the decision makers. They go, well, there's a lot of money in it. Yeah, there is, right now at least, and hopefully that'll remain true for at least another 20 years or so. Yes, one of the best careers you can get to with the least education. A 4-year degree in computer science will get you a starting salary around $100,000. That's not true in just about any other discipline. So it's an incredible opportunity for students. And there's an equity issue here too, right? Which students right now are the ones who have access to that opportunity? Well, it's a lot of white and Asian boys. That is, if you look into a lot of high school classrooms, that's what you tend to see. So there's an equity question too. And it's not just race and gender, it's also geographic distribution. My organization, TEALS, is starting to work a lot more in rural areas and in the middle of the country where we don't traditionally think about technology and tech companies, but it's important there too. So that's one reason. It's a good reason. There's a flip side of that opportunity argument, which is you talk to any company that uses technology and they will tell you they have a really hard time hiring talented computer scientists, programmers, and technologists. You wouldn't think that's true, but they have a very hard time. They'll put it in one of their top 3 challenges to their business. So we need more people going into this field for the good of our economy, for the good of our national security, right? For the good of the country. But not every student who studies computer science is going to become a software engineer, and that's fine. Because of these 2 other reasons. Basic literacy. And I'll talk a little bit about these in more depth, but there are things, just like in biology, there are things that you can access from studying biology that are really applicable across the board to other important things. That's true in computer science too. And we'll talk about computational thinking in a minute. But I also want you to think about this idea that in the 21st century, right, there are, I can't even count how many digital devices there are, how many artificial brains there are in this room. There are more than I can count. There's probably one in each of those microphones. There's one in that little display that's on your table that controls something about what the monitor in front of you is showing. Each of your computers and cell phones has one. These devices up here, this camera's got one. My watch has an artificial brain in it. Okay? These things are all around us. They act in sometimes unpredictable ways. They've been crafted to show you as if they are different than they actually are. As a user, these machines are lying to you. They make you think that they are a watch. This is making me think it's a watch. It's not a watch. It's not, it's a lie. It's not a watch. And if I don't understand that, then when something weird starts happening, when this is suddenly an hour off from how I expect it to be, I won't understand why. Right? Basic things like that. But really other important things. We still live in a semi-functioning democracy. Right? We elect the leaders who make the laws. And if those leaders don't understand how this technology works, and we don't understand how it works, we're going to make some really weird laws. Like laws that say that maybe it's okay for the government to take data that lives in Ireland and have a US search warrant that accesses that data in Ireland. How does that work? You couldn't do that if the data was in someone's file cabinet, but you can do it if the data is online. Is that okay? Or that Apple should have to update their operating system in a way that makes it possible for the FBI to break into someone's phone. Is that a good idea? I don't know. If you think of a phone as like a lock with a key, you might think that's an okay idea. Well, you just need to make one key that can open that one lock. But that's not how software works. You can't do that. And if you don't understand a little bit about security and cryptography, you won't understand why that's a terrible idea. So basic literacy for our society. And then this last one, computational thinking. Has anyone heard that term before? Raise your hand. Okay, a few people. Anyone want to give a go at what it is? This one's even harder than computer science. Anyone? Brave souls? Free donut if you... So here's a good definition. Computational thinking is the thought processes involved in formulating a problem and expressing its solutions in such a way that a computer, or a human or a machine computer, could effectively carry it out. In other words, it's the problem-solving skills you need to solve the types of problems that computers can solve. Sort of a circular definition. But there's a certain set of problems that things like computers can solve, and computational thinking is how you can go about doing that. I know that's a little bit of a roundabout definition, so I'll try to make it a little more concrete, although it's hard, and I might draw some things. So these are generally the 4 big areas in computational thinking. Decomposition, pattern recognition or data representation, abstraction or generalization, and algorithms. We've talked a little bit about algorithms already. An algorithm is sort of a method for solving a certain type of problem. So being able to create and reason about algorithms is computational thinking. Algorithms don't have to be computer code. Algorithms could be the routine that you use in the morning to figure out what to wear. Right? How do I decide what to wear? Well, if it's cold out, I should probably wear long pants and not short pants. Right? If I wore that yesterday, I probably should not wear that today. There's a set of logical rules and a formula that I apply to decide what to wear today. Right? That's an algorithm. It doesn't have to be something super complicated. Decomposition is a pretty easy one to understand. Not biological decomposition, but just taking things apart. Being able to understand a big thing by taking it apart and figuring out what it's made of. That could be a computer. What are the parts of a computer? Well, it's a screen and a keyboard and an input device of some kind and maybe some sound devices. There's a processor. There's a memory and a hard drive. Right? That's decomposing a computer into its parts. One of the magical things about computer science is that usually when you take things apart into parts, you can do that again and again and again. What's a hard drive? Well, a hard drive is made up of a spinning platter that has magnetic cells on it and an arm that can read the value of those different magnetic cells. Okay, well, what's that magnetic platter made out of, right? You can just keep taking things apart like that and learning more and more. We do the same thing in software, not just hardware. Abstraction is kind of the opposite. Abstraction is like, how do I take something complicated and describe it in simpler terms? One of my favorite examples of abstraction, I'm going to pull up a web page real quick. Here's a web page that you have all used before. At least I think you have. Come on, you can do it. There we go. All right, Google Maps. Here we are. Here we are in New Haven. It knows where I am. That's a little creepy, right? What happens when I zoom in? What just happened? Did you see that? It flashed and something changed.
More details.
More detail. Interesting. So the map changed because of how close I was zoomed in. If I zoom out, we're going to start losing detail. Okay, there goes some of the buildings. There goes some of the street names. There goes some more street names. Once I get a little further out, the streets themselves, a bunch of the streets are gone. We just have the big streets. The further I go, the less detail I have. That's abstraction. Someone is deciding which details are relevant depending on how closely I want to look at it. We've got a more abstract representation when I'm more zoomed out and a more concrete representation when I'm zoomed in. That's one kind of abstraction. Now I have to remember how to turn this back to the other way. Yeah, but then it does that and it's frustrating. Hold on. Okay. Pattern recognition. You guys do this in math class. You do this in lots of classes. The ability to look at a problem or look at a solution and say, oh, these two things are very similar. I wonder if I could solve them the same way. Or I wonder if I could structure a solution by taking advantage of the relationship between these two things. For example, if I were trying to create an algorithm for making a peanut butter and jelly sandwich, it would probably have a lot in common with an algorithm for creating a grilled cheese sandwich. In both cases, I've got to find some bread. I'm probably going to need a knife. I might cut some things. But then there are parts that aren't in common, so you have to be able to recognize where's the pattern, where isn't a pattern. Very, very important in computer science. The flip side of pattern recognition is deciding how to represent something. So if I'm trying to make a robot that knows how to make a peanut butter and jelly sandwich, I have to decide, how do I represent the world to that robot? What does the robot need to be able to understand about the world? Does the robot need to understand all the little flecks and seeds within the strawberry jelly? Probably not. Probably doesn't care about that. But it does need to understand bigger things, like how to unscrew a bottle, and the fact that there's something called a lid, which could be on top of that bottle. If it doesn't understand that and it goes to spread the peanut butter, it's going to run into a problem. So data representation is really important. So these are some of the areas of computational thinking. Now, real quick, I'd love to just run around the room and have people share, what do you teach? What subject or subjects? Most of you probably teach many subjects. Do you teach? Let's just really quickly, like two-word answer. We're going to go all the way around. We have students over here.
6th grade, all subjects. Is that what you wanted?
Yep.
I'm a coach for pre-K, 5th grade students.
All subjects.
Yeah.
Yep.
3, 4, 5, math, and reading instruction.
Great.
Pre-K to 8, art, visual art.
7th and 8th grade, world cultures and American history.
Great.
3 to 9 to 12, computer science and computer math.
Wonderful.
Pre-K to 8th science.
Okay, it sounds. Let's go to the back.
I teach computers pre-K through 5.
Computers pre-K through 5.
I'm an assistant principal.
Assistant principal.
Introduction to computers, 2 through 8.
2 through 8.
7, 8 computers.
7 computers.
8th grade math.
8th grade math.
Middle school library media specialist.
During the year pre-K, during the summer K-2, and homeschool my kids.
Very cool.
Kindergarten also.
Library media K-5.
Science 7th grade.
7th and 8th grade ELA. 4th grade everything but science.
7th grade math. 7, 8, 9.
A little bit of everything, right? So for a minute, I want you to think about these areas of computational thinking. And again, jot down, which of these do you recognize from some of the pick one of the subjects that you teach for a minute. Which of these areas apply to that subject? I guarantee at least one of them does. It would be very hard to think of a subject where you couldn't apply one of these areas of computational thinking. Go through the exercise. Like actually think about a lesson, maybe something you did this last week, right? Did it have one of these components, or could it have one of these components? Anyone got an example? Yeah.
Well, in 4th grade we teach multiplication and partial products. So if you're multiplying 456, you would decompose 456 to 400 plus 50 plus 6 and multiply it by a number.
Absolutely.
And we
So-
use that term, decomposition.
Yeah, very common way of solving a big problem is to chop it up into smaller problems and then reason about the smaller problems. Or not even smaller, but just ones I already know how to solve. I know how to think about 6. 456 is a little scary, but 6, I know a lot about 6. That's a computer science behavior. That's a thing we do in computer science all the time. And we don't just do it, we think about it. We talk about it. We have ideas around that process. Anyone else have an example? Yeah, Brian.
Abstraction and generalization. I'm teaching about ecosystems at different levels. And so you're abstracting up to the big ecosystem and then down to like just a stream in part of it. And looking at the different levels of...
One of my favorite computer science labs that I've ever seen, it was using language like Scratch. Some of you might use Scratch later today. And students were creating a model of vaccination. And so they created these objects inside of their computer model representing a bacteria or a virus or something. And they had variables that could make there be a higher concentration of the disease or a lower concentration. And then a variable that could be a higher concentration of the vaccine or the antibody and a lower concentration of the antibody. Right? So to create that model, they had to think about the abstraction. Okay, what objects are important to what I'm trying to study or trying to analyze and model here? Well, I need the disease and I need the antibodies. And what properties of those objects are important? Well, how many there are, how resistant they are, how, so figuring out what's important to include in the model. That's abstraction. And that's incredibly important to any form of modeling you might do. We do modeling in social studies, right? We do modeling in art and design. We do, right? This stuff's everywhere. So the last thing I'm going to leave you with in this talk, some teacher nerdery. I just saw a talk by this guy, Phil Bagg, who is British. If you want me to enjoy your talk, be British. Anything sounds better in a British accent, which kind of explains Tony Blair. So this website is some work that Phil Bagg and Professor Mark Dorling have done. And this is problem-solving attitudes and how they relate to computational thinking. So they've defined this on the left, this first column. These are categories and behaviors involved in problem solving. Right? To be good at problem solving, you need to cope with complexity, handle ambiguity, deal with open-ended problems, be able to adapt, evaluate, investigate, persist, and communicate. These are sort of behaviors that are important to solving problems. The other columns are just examples of attitudes that we want students, or skills that we want students to have. I can statements, right? I can adapt existing ideas to solve new problems. I can develop, test, and debug until a product is refined. And they're categorized based on the rows. And then the really cool part is the color coding represents the different areas of computational thinking. And so these problem-solving attitudes and behaviors relate very directly to computational thinking and therefore computer science. So this is showing you this connection between this discipline, computer science, and problem solving, which as we know is a part of basically every domain. One last thought I want to leave you with. When I started getting involved in computer science education, I had this doe-eyed belief that if we just taught kids coding, they would do all of these things automatically. They would have to in order to code. It's not true. not only do I know it's not true after I started trying to do it, there's research. It's not true. Transfer is real, and students can absolutely transfer skills around problem solving that they learn in computer science to the general domain or to other specific domains, but it only happens if your practice of coding, computer science, programming explicitly centers on these problem solving attitudes and behaviors. So as you think about integrating computer science in your classroom, there's lots of reasons. I hope you've gotten some great reasons why you should do that. You're here, so you probably already were thinking about it. But I hope now you have some great reasons. But I want to leave you with this, which is coding is great on its own, but it's even better if you can center it into these very important general ideas of problem solving. This is what creates critical thinkers. This is what creates problem solvers. This is what creates people who can really thrive in a complicated 21st century world. So I hope that you can think about these areas and behaviors as you are thinking about adapting computer science into your classroom, or just going about all of the teaching that you do. I think these things are critically important. This website here, code-it.co.uk/attitudes, has this and a whole bunch of other related resources to this attitudes and problem-solving behavior work. I also should have put my email address on here, but I will do that now using this nifty pen. No, I won't. It was working beforehand. And there we go. NGRANOR at micro. Oh gosh. What just happened? What is happening?
Technology.
Yeah, technology. Yeah. You'll send it out. All right. Well, it's Microsoft. You can probably remember that. Why? It's weird. It's just disappearing. Anyway, as you go throughout the day, I'm going to be here. I'd love to talk to you at lunch. I'd love to talk to you after the fact. Send me an email if you have more questions. And thank you for being here.
One other thing really quickly about Nathaniel that we failed to mention earlier is that he's the whole reason Codehaven started. He contacted us, I think, 2 years ago and said, oh, we've got this teacher at Fairhaven who's interested, and connected us and Dave, and so we're so grateful that he's here today, and also that he's supporting Codehaven.
Thank you.
We definitely wouldn't be here.
I'm going to throw that right back at you, just to say that all I did was made a connection and put some really talented and passionate people together. And I'm so proud and thrilled of what they've built in the last year and a half, including this conference today, which really has not involved huge amounts of my input, but it's just so impressive. So the lesson here for teachers is if you want something, find someone who has it and ask them. Because more often than not, they want to help you get that thing. So, all right.
Great. So thank you so much, Nathaniel.